just confirm me whether my voice is audible or not. Just confirm it once.
सोचना कैसा?
My voice is audible to you? So, a very good evening, everyone. First of all, such a big congratulations to all the Indians out there. We landed safely on Chandrayaan 3, right? We landed safely on Moon through Chandrayaan 3. It was such a proud moment for all of us. ISRO did it once again. Very good evening, everyone. First of all, ISRO did it once again for us, right? Now just have this feeling working for such a reputed organization like ISRO. And again you have a chance to work for such an organization through cracking examination like GATE and the competitive technical exams conducted by ISRO. Okay, that's why these examinations are of so much importance. When you look into the engineers that are present in the country right now, we are directly contributing into the nation building projects. It can be like working for any public sector undertakings. You just imagine the kind of projects handled by these public sector undertakings. It can be the densest road network managed by NHAI. It can be the oil refineries of our country. It can be the power plant of our country. It can be the nuclear power plant of our country. Everything is managed by these public sector undertakings. And there is a golden opportunity to enter in these public sector undertakings through GATE examination. That's why this examination is such a reputed exam in the country. And preparing for such a reputed examination requires a lot of hard work. It requires consistency. That's why we came up with this series of excellent questions that are expected for GATE 24. Myself Prateek Mishra, and I welcome you to the YouTube platform of IMS GATE Academy. Today we will going to deal with a very important topic of environmental engineering, that is wastewater quality parameter. Usually, my dear students, in civil engineering and also for the second paper of environmental engineering, we have seen a lot of questions asked from this domain. And every year, for sure and short reasons, there has to be one question from this area. That is the wastewater quality parameters, right? So today we will going to see few important questions. Mostly my thing is to make you aware about the concepts, through the questions, okay? So these questions that I have taken today are designed in such a way that entire concept will be revised if you practice these questions that we will be going to do in this session, okay? So my thing for this session is, I'll be giving you the question, I'll be giving you some time to solve the question, at least analyze what is asked in the question, and then we will solve it together, okay? So let's start with the very first question of wastewater quality parameter. This is the question from theoretical oxygen demand. I'll keep the timer for you. The timer will be of 2 minutes and you need to solve this in this stipulated time. So this is my timer. Timer is for 2 minutes for you. Just try this one. And your time starts now. Just go through this. Chalo, time's up. Let's see this question. This is a question from theoretical oxygen demand. It says that a sample of water contains organic compound. The chemical formula for organic compound is given to us. C6H12O6. We know this. This is glucose. At a concentration of 10 raised power minus 3 moles per liter. Please keep a check on the unit. C6H12O6. Concentration is given as 10 raised power minus 3 moles per liter. Okay. The theoretical oxygen demand of water in gram of oxygen per liter rounded off to 2 decimal places is. Okay. So first of all, what do you understand by theoretical oxygen demand? If we know the exact chemical formula of the organic matter, then after writing the balanced oxidation equation for the organic matter, through that equation we can calculate amount of oxygen required to oxidize this organic matter. For example, here the organic matter is C6H12O6. We know the chemical formula. So first step is I'll write down the oxidation reaction for this. Oxidation reaction is C6H12O6 plus oxygen. This will give me carbon dioxide, CO2 plus H2O. Now step number 2 is you have to balance this entire equation. Okay. Now for balancing this entire equation, this is 6O2. This will going to give me 6 CO2 plus 6 H2O. You have to just add up all the carbon atoms that are present on the reactant side, and this should be equal to the number of carbon present on the product side. Similarly, you need to add up all the hydrogen present on the reactant side, and that should be equal to the number of hydrogen present on the product side. Similarly goes with the oxygen. So for all the elements or all the atoms that are present on the reactant side should be equal to the number of all the reactants of same species present on the product side. This balancing equation we already know, right? We did a lot in chemistry in 11th or 12th class. Now from this equation, I can write 1 mole of C6H12O6 requires 6 moles of oxygen. Requires 6 moles of oxygen to oxidize. Okay. In the system, the concentration of C6H12O6 is 10 raised power minus 3 mole per liter. So this many mole of glucose will require this multiplied by 6 moles of oxygen. So 10 raised power minus 3 moles of C6H12O6 requires 10 raised power minus 3 into 6 moles of oxygen. Now this much amount of oxygen is required to oxidize this much amount of organic matter. 10 raised power minus 3 moles of organic matter will be oxidized by this much amount of oxygen. So this is known as theoretical oxygen demand. This is known as theoretical oxygen demand, THOD. And this is what asked in the question. So I will write down THOD. THOD is equal to 10 raised power minus 3 into 6 moles per liter. Moles per liter. But we need to represent this in gram per liter of oxygen. So 1 mole of oxygen contains how many moles of 1 mole of oxygen, the weight of 1 mole of oxygen is equal to, oxygen is 16, so 16 into 2 grams. This is the weight of 1 mole of oxygen. So this many moles of oxygen will going to weigh in grams, so that we need to calculate. So THOD comes out to be 10 raised power minus 3 into 6 into 16 into 2. So this is the amount of oxygen in grams per liter required to oxidize 10 raised power minus 3 moles per liter of organic matter. Just calculate this and tell me the answer. This is 6 into 32. So this comes out to be 192 into 10 raised to power minus 3 gram per liter. This 10 raised to power minus 3 and gram, this will be milligrams. This will be milligrams, right? So THOD comes out to be 192 milligram per liter. This comes out to be 192 milligram per liter. This is my final answer. So this is my final answer for first question, right? Okay. Now coming to the next question. This is the question from BOD and TOC. This is again a very important question. It was asked in GATE this year. These varieties of questions are like one of the favorite varieties of questions that can be framed from this topic, where two or more parameters are used. Just read this question. I'll give you a 1 minute time to analyze what is actually asked in the question, not more than 1 minute. You have to only analyze what is there in the question. Okay. So the question is saying the theoretical aerobic oxidation, please mark this word, aerobic oxidation of biomass, this is the biomass C5H7O2N, is given below. This is the oxidation equation for this biomass. The biochemical oxidation of biomass is assumed as the first order reaction with rate constant of 0.23 per day. This is the value of K at 20 degrees Celsius with logarithmic base E. Neglecting the second stage of oxygen demand from it, biochemical oxidation, the ratio of BOD5 at 20 degrees Celsius to the total organic carbon TOC of the biomass is. So basically you need to calculate the value of BOD5 to TOC ratio, right? Now first of all, when you observe this organic matter, how to calculate TOC, total organic carbon. So when you see this organic matter, 1 mole of this organic matter contains 5 mole of the carbon. Just by looking into the chemical formula, we can identify that how much amount of carbon is present. So first I will calculate TOC, total organic carbon. So chemical formula for organic matter is C5H7O2. This is C5H7O2N. This is the organic matter, right? Now 1 mole of this organic matter, 1 mole of this organic matter C5H7O2N contains 5 moles of carbon. Contains 5 moles of carbon, right? So from here I can calculate the total quantity of carbon that is present in 1 mole of this organic matter. So 1 mole of C5H7O2N contains 5 into converting this moles into grams. So you need to multiply it by the atomic weight of carbon, which is 12. So 5 into 12 grams of carbon. So 1 mole of this organic matter contains 5 into 12, which is 60 grams of carbon. So total organic carbon, TOC, is this value. This is the value of your TOC. Means the quantity of carbon which is present in 1 mole of the organic matter. So TOC is equal to 5 into 12 gram of carbon present in 1 mole of the organic matter. So TOC comes out to be 60 gram per mole. This is the value of TOC, total organic carbon, 60 gram per mole. Now the second thing that you need to calculate is BOD5. For calculating BOD5, either the test of BOD should be given to you. The second way is, if you know the value of BOD ultimate, from that also you can calculate the value of BOD5. Okay. So let's start with this. What is BOD ultimate? BOD ultimate is the total amount of oxygen which is required to oxidize the organic matter. And this BOD ultimate can be calculated using this oxidation reaction. Because from this oxidation reaction, it is clearly visible that 1 mole of this organic matter requires 5 mole of oxygen for its complete oxidation. And this 5 moles of oxygen is nothing but the total amount of oxygen required to oxidize this organic matter, which is known as BOD ultimate. So I'll start from here. 1 mole of C5H7O2N. I think this is the chemical formula, yeah. 1 mole of this organic matter requires 5 moles of oxygen. Right? So 1 mole of this organic matter, C5H7O2N, requires 5 into molecular weight of oxygen. So what is the molecular weight of oxygen? Oxygen is 16. 16 into 2 is 32. So 5 into 32 grams of oxygen. So 1 mole of this organic matter requires 5 into 32 grams of oxygen. Now this 5 into 32 grams of oxygen is nothing but your BOD ultimate. This is your BOD ultimate. That is the total amount of oxygen required to oxidize the biodegradable organic matter. So from here BOD ultimate comes out to be 5 into 32. 5 into 32, which is 160 gram per mole. This is your BOD ultimate. Now from this BOD ultimate, you can calculate BOD5. So BOD5 is equal to BOD ultimate into 1 minus e raised power minus k into 5. Here the time you should take is equal to 5. The value of k is given to you, BOD ultimate you have just now calculated. So the value of k is 0.23 per day. Substitute all the values. So this is 160 into 1 minus e raised power minus 0.23 into 5. From here you can calculate BOD5. So this is e raised power minus 0.23 into 5. 1 minus answer multiplied by 160. So this comes out to be 109.34. So BOD5 109.34 milligram per liter. You have the value of BOD5, you have the value of TOC. Now you have to just take the ratio which is asked in the question. You need to take the ratio of BOD5 to TOC. So the ratio of BOD5 to TOC, this is equal to 109 point, how much? 34. Divided by TOC. I think this is 60. Let me check. TOC that we have calculated is 60, right? So this is your, okay. So this is not milligram. This is gram per mole. This is gram per mole, right? So 109.34. 109.34 divided by 60. This comes out to be 1.822. So BOD 5 to TOC ratio. This comes out to be how much? 1.822. This is my final answer. Okay, so I hope you have also understood this question. Moving on to the next question. This is the next question. Again, take 2 minutes of time and try to solve this. Just take 2 minutes of time and try to solve this. Okay, let's solve this. Now, this type of question is again a highly expected question in GATE examination. Basically, in this type of question, what they do is they will give you 2-3 species. For example, let's read this question first. A wastewater sample contains 2 nitrogen species. Okay, a wastewater sample contains 2 nitrogen species, namely ammonia and nitrate. So, in a wastewater sample, ammonia and nitrate are present. This is my wastewater sample. In this wastewater sample, ammonia NH3 and nitrate are present, NO3 minus. Okay. In this wastewater sample, ammonia is present and nitrate is present. The atomic weight of hydrogen, nitrogen and oxygen is given to you. In this wastewater, the concentration of ammonia is 34 milligram per liter. So, this is 34 milligram per liter, concentration of ammonia. Next, the concentration of nitrate is 6.2 milligram per liter. So, this is given as 6.2 milligram per liter. The total nitrogen concentration in this wastewater in milligram per liter would be. So, you need to calculate total nitrogen concentration. Good evening, Tushar. Good evening. You need to calculate the total nitrogen concentration that is present in this wastewater sample. Now, my dear students, basically what happens is we get a lot of confusion. We do not understand actually what we need to calculate after reading this question. Okay. Now for this variety of question, concept is very simple. Here you are asked to calculate nitrogen concentration. So first thing is calculate the number of moles of nitrogen that are present in ammonia and that are present in nitrate. After calculating the number of moles of nitrogen present in ammonia and nitrate, just add the total number of moles to get the total number of moles of nitrogen present in the wastewater sample. And then multiply it with the atomic weight of nitrogen to get the concentration of nitrogen. This is one of the way of asking the question. The question is only wanting you to calculate number of moles of nitrogen. Okay. When we will see this, you will get clarity. We will start with this. First, we start with ammonia. First, we will start with ammonia, NH3. For ammonia, the concentration of ammonia is given as 34 milligram per liter. This is 34 milligram per liter. This is the concentration of ammonia. From this concentration of ammonia, the first thing we should calculate is number of moles of ammonia that are present. So number of moles of ammonia that are present in the wastewater is equal to the given weight of ammonia. The given weight of ammonia is 34 milligram. So I will write 34 into 10 raised to power minus 3. So now this will be in gram per liter. Divided by the molecular weight of ammonia. So molecular weight of ammonia is nitrogen 14 and hydrogen is 1. So 3 into 1. So this is 14 plus 3 into 1, that will be 3. So these are the number of moles of ammonia that are present in the wastewater sample. So this comes out to be 2 into 10 raised to power minus 3 moles. So this many moles of ammonia are present in the wastewater sample. Now from this ammonia, we can clearly identify that 1 mole of ammonia contains 1 mole of nitrogen. 1 mole of ammonia contains 1 mole of nitrogen. Right? So this many moles of ammonia will contain same number of moles of nitrogen. So 2 into 10 raised to power minus 3 moles of ammonia contains 2 into 10 raised to power minus 3 moles of nitrogen. So these are the number of moles of nitrogen that are present in the wastewater in the form of ammonia. Okay. Similarly, we will calculate the number of moles of nitrogen that are present in the form of nitrate. So the concentration of nitrate is 6.2 milligram per liter. So I'll start with this. Nitrate concentration is NO3 minus. Nitrate concentration is 6.2 milligram per liter. So number of moles of nitrate, NO3 minus, this is equal to the given weight of nitrate, which is 6.2 into 10 raised to power minus 3. I'll convert this milligram into gram because the molecular weight, whenever we are substituting, that is always in grams. So this is 6.2 into 10 raised to power minus 3 divided by the molecular weight of nitrate. So molecular weight of nitrate is nitrogen 14 plus oxygen 16 into 3. This is the molecular weight of nitrate. Okay. When you solve this, you will get the number of moles of nitrate, right? Can you just quickly solve this and get me the value of number of moles of nitrate? 6.2 into 10 raised to power minus 3 divided by 14 plus 16 into 3. I think this will be 62. So 6.2 divided by 62 will be 0.1. So number of moles of nitrate will be 0.1 into 10 raised to power minus 3. So these are the number of moles of nitrate. Now again, by looking into the molecular formula of nitrate, 1 mole of nitrate contains 1 mole of nitrogen. Contains 1 mole of nitrogen. So these many moles of nitrate will contain same number of moles of nitrogen. So 0.1 into 10 raised to power minus 3 moles of nitrate contains 0.1 into 10 raised to power minus 3 moles of nitrogen. So these are the number of moles of nitrogen that are present in the form of nitrate. Okay. These are the number of moles of nitrogen that are present in the form of ammonia, and these are the number of moles of nitrogen that are present in the form of nitrate. Now you have to just add up to get the total number of moles of nitrogen present in the system. So total number of moles of nitrogen present in the wastewater sample is number of moles of nitrogen present in the form of ammonia, this is 2 into 10 raised to power minus 3, plus number of moles of nitrogen present in the form of nitrate. So this is 0.1 into 10 raised to power minus 3. So the total number of moles of nitrogen will be 2.1 into 10 raised to power minus 3. These are the total number of moles of nitrogen present in the wastewater sample. From here I can calculate the nitrogen concentration. So nitrogen concentration is simply number of moles multiplied by the atomic weight of nitrogen. So nitrogen concentration is number of moles 2.1 into 10 raised to power minus 3 multiplied by the atomic weight of nitrogen, which is 14. So this will going to give me the concentration in gram per liter. This 10 raised to power minus 3 and gram will be in milligram. So you have to just multiply by 2.1 into 14 to get the final answer. So this is 2.1 into 14. So this comes out to be 29.4 milligram per liter. This is my final nitrogen concentration, 29.4 milligram per liter. This is my final nitrogen concentration. So these type of questions are like a favorite varieties of questions. Okay, what change they can do is, instead of nitrogen, they can ask you to calculate the sulfur concentration. They can ask you to calculate the phosphorus concentration. They can ask you to calculate the hydrogen concentration, right? So every time, whenever you are dealing with these type of questions, you have to take the mole concept into picture. You have to calculate number of moles of that particular species, and then you have to just add up all the number of moles and multiply it with the atomic weight of that particular species. Here that species is nitrogen, so we have multiplied by 14. Okay. So I hope you have understood this. Moving to the next question. Just try this one. This is a very good question. I'll take you 2 minutes time. You try this. And your time starts now. This is the timer I have. Okay, let's see this. This is again a most asked variety of question. When you see the question paper of environmental engineering and civil engineering, you will find a lot of question from this variety where a sewage stream is meeting a river stream. In fact, an entire topic of disposal by dilution in river stream is there in the wastewater engineering. That's why this is a very important topic. Okay, the question says that a river has a flow of 1000 million liters per day. So this is 1000 mld. BOD 5 of 5 milligram per liter and DO level of 8 milligram per liter before receiving the wastewater discharge at a location. Means a river is flowing like this. Okay, I'll draw the river like this. This is the river which is flowing. This is the river which is flowing. And the discharge of the river is given as Q of river. I'll write this Q of river. This is given as 1000 mld. Q of river is 1000 mld. Then next, BOD 5 of river is 5 milligram per liter. BOD 5 of river is 5 milligram per liter. This is 5 milligram per liter. Next, DO of river is 8 milligram per liter. DO of river is 8 milligram per liter. This is 8 milligram per liter. Okay. This is the data for the river when it is not getting mixed with the sewage stream. Now what happens is wastewater discharge of 100 mld with BOD 5 of 200 milligram per liter and DO of 2 milligram per liter falls at the location. Into this river, a wastewater stream is getting mixed. So this is the wastewater stream that is getting mixed. This is the sewage stream. This is my sewage stream that is getting mixed into the river. So this is the junction where river is getting mixed with the sewage. So beyond this junction in the downstream side, this is the mix of river and the sewage stream. On the upstream side of this section, you have pure river and pure sewage stream. But on the downstream side of this section, you have the mix. Okay. For the sewage stream, certain data is given to us. So for sewage stream or wastewater stream, so for sewage stream, certain data is given to us. The discharge of the sewage stream is given as, so I will write down QS, this is sewage stream. This is given as 100 mld, 100 million liters. Next, BOD 5 of this sewage stream, BOD 5 of this sewage stream, this is given to us as how much? 200 milligram per liter. So this is 200 milligram per liter. Next, DO of that sewage stream is equal to, DO of the sewage stream, this is equal to 2 milligram per liter. DO of the sewage stream is 2 milligram per liter. Next, assuming the complete mixing of the wastewater and the river, the immediate DO deficit in milligram per liter rounded off to 2 decimal places is, okay. So you need to calculate the oxygen deficit, and here you are given with the value of saturation dissolved oxygen, which is 10 milligram per liter. So I will write down here DO saturation. I'll use some other color. So DO saturation is equal to 10 milligram per liter. This is the value of DO saturation. What you need to calculate? You need to calculate oxygen deficit of this mix. So first of all, what is this oxygen deficit? Now, by the definition of oxygen deficit, what we mean is by how much amount DO level in the mix is less than the saturation value. That is what we mean by the oxygen deficit. Oxygen deficit of the mix simply means by how much amount DO of the mix is less than the saturation value. So what is oxygen deficit? Oxygen deficit of mix. Oxygen deficit of mix. So this is D mix. Oxygen deficit of mix. This is equal to the difference between DO saturation minus DO of mix. Means by how much amount DO of mix is less than the saturation value. So step number 1 is calculate DO of mix. So DO of mix, dissolved oxygen of mix is equal to DO of river stream multiplied by discharge of river stream plus DO of sewage stream multiplied by discharge of sewage stream divided by discharge of river stream plus discharge of sewage stream. Okay. So basically whenever two things are mixing together, then the value of mix is the weighted average with respect to their discharge. For example, we need to calculate DO of mix. So DO of mix is the weighted average. You see the weight with respect to the discharge. DO of the river multiplied by discharge of the river. DO of sewage stream multiplied by discharge of sewage stream divided by total discharge. So from here we will calculate DO of mix. DO of mix. So DO of river is how much? 8 milligram per liter. This is 8 milligram per liter multiplied by discharge of river, which is 1000 mld, plus DO of sewage stream. How much? This is 2 milligram per liter. This is 2 milligram per liter multiplied by discharge of sewage stream, which is 100 mld, divided by 1000 plus 100. So like this you calculate DO of mix, right? Just do the calculation. So this is 8000 plus 200. So 8200. 8200 divided by 1100. So 7.45 is DO of mix. DO of mix is 7.45 milligram per liter. So DO of mix we know. From DO of mix we can calculate the initial oxygen deficit or oxygen deficit of the mix. Oxygen deficit of the mix. So oxygen deficit is equal to DO saturation. What is the value of DO saturation? This is 10 milligram per liter. It is given to us. Minus DO of mix, that is 7.45. So 10 minus 7.45. 10 minus 7.45. This comes out to be 2.55 milligram per liter. So this is my final answer for DO of mix. Sorry, oxygen deficit of mix. 2.55 milligram per liter. So oxygen deficit basically tells us by how much amount DO value in the mix is less than the saturation value. Okay. Now moving on with this, try this one. This is question of BOD. This is the question of BOD. Try this one. The question says that if the BOD3 of a wastewater sample is 75 milligram per liter and reaction rate constant to the base E is 0.345 per day. So I will write down. I will write down all the things. BOD3 is given to us as 75 milligram per liter. This is 75 milligram per liter. And the value of K is given as 0.345 per day. This is the value of K. BOD3 is given and the value of K is given. The amount of BOD remaining in the given sample after 15 days is. So you need to calculate BOD remaining after 15 days. You need to calculate BOD remaining after 15 days. First thing is given to you is the value of BOD3. This BOD3 is the BOD consumed, right? This BOD3 is BOD consumed. BOD consumed in 3 days. This is BOD consumed in 3 days. Okay. And this is what they are asking is BOD remaining after 15 days. So this you need to calculate. So we will start with this. First of all, for calculating BOD remaining after 15 days, the expression that we will use is BOD remaining after 15 days. This is equal to BOD ultimate into e raised to power minus K into 15. This is the expression for BOD remaining, right? The expression for BOD3, and this is the consumed BOD. BOD3 consumed. This is equal to BOD ultimate into 1 minus e raised to power minus K into 3. This is the expression for BOD3 consumed, right? Now, either you can solve for BOD ultimate, you substitute the value of BOD3, 75 milligram per liter, you know the value of K and calculate the value of BOD ultimate. Then take this BOD ultimate and substitute here to get the value of BOD remaining. That is one way of solving this question. The next way of solving this question is to just divide these two equations. When you divide these two equations, this BOD ultimate and BOD ultimate will going to cancel out. And this will going to save a lot of time. Literally, you have just eliminated one equation like this by dividing these two expressions. Okay. Now you just substitute the value. So BOD remaining after 15 days divided by BOD consumed after 3 days. This is 75 milligram per liter. This is equal to e raised to the power minus 0.345 into 3. This is this is 0.345 into 15 divided by 1 minus e raised to power minus 0.345 into 3. Numerator and denominator. You can solve this to get the final answer. You can just solve this to get the final answer, right? BOD3 is 75 only, yeah. And K is 0.345, yes. So you just solve this to get the final answer. So this comes out to be e raised to power minus 0.345 into 3. 1 minus answer, 1 divided by answer into e raised to power minus 0.345 into 15 into 75. So this comes out to be BOD remaining after 15 days. This comes out to be 0.658 milligram per liter. This is my final answer. BOD remaining after 15 days is 0.658 milligram per liter. So this is my final answer, right? So basically this is the easier method to do this. Just take the ratio of these two equations, or in the next thing that you need to do is, means the other method or the other way to deal the same question is, write down the expression for BOD3, calculate BOD ultimate, and then substitute BOD ultimate in this equation to get the value of BOD remaining. By taking the ratio, we have just eliminated that step. Okay. Chalo, moving on with the next question, try this one. I'll give you 2 minutes time. You can try this one. Meanwhile, students, you can check on our description box and you can join our Telegram group for daily quizzes. The link is there in the description box. You can just check on that. Okay, time's up. Let's see this. So this is the question from biochemical oxygen demand. What question says is, a student began the experiment to determine 5-day BOD at 20 degrees Celsius on Monday. Okay. He began the experiment on Monday. Since the fifth day fell on Saturday, the final DO reading were taken on next Monday. He started the experiment on Monday. Right? He started the experiment of Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. So this is the fifth day. Where he was supposed to take the reading. Remember, when we talk about calculating the BOD, we measure DO initial and then we measure DO final. And BOD 5 is equal to DO initial minus DO final multiplied by the dilution factor. So ideally, he was supposed to take DO final value on the fifth day. But since the lab was closed on Saturday and Sunday, he took the reading on next Monday. Now this next Monday is the seventh day. And on this seventh day, he took the DO final value. Okay. He was ideally supposed to take on the fifth day, but he took on the seventh day. Now from this, he calculated BOD, and that BOD is BOD 7 at 20 degrees Celsius. BOD 7 at 20 degrees Celsius, and this was calculated as 150 milligram per liter. This is the BOD 7 value, which is 150 milligram per liter. This is 150 milligram per liter. This is the BOD 7 value, right? Now the question is asking, what should be the 5-day BOD at 20 degrees Celsius? The value of K to the base E is given as 0.23 per day. he has calculated BOD 7, okay, because there are limitations with respect to observing the final dissolved oxygen value. And he is asking us to calculate BOD 5. Okay, let's see this. So BOD 7 is given to us, the value of K is 0.23 per day. I think so this is the value. The value of K is 0.23 per day to the base E. And we are asked to calculate BOD 5 at 20 degrees Celsius. This we need to calculate, okay. Again, there are two methods to do this question, but we will deal with the simple method. First one is BOD 7 at 20 degrees Celsius. This is equal to BOD ultimate into 1 minus e raised to power minus K into 7, okay. Because this is the BOD consumed in 7 days at 20 degrees Celsius. Similarly, I can write down the expression for BOD 5. So BOD 5 at 20 degrees Celsius is equal to BOD ultimate into 1 minus e raised to power minus K into 5. Okay. Now again there are two methods. Method 1 is, from this first equation, you calculate the value of BOD ultimate and you substitute here to get the value of BOD 5. Or second method is the simple method where you just take the ratio of these two values. So this BOD ultimate and BOD ultimate will going to cancel out. BOD 7 at 20 degrees Celsius, this we know, 150 milligram per liter. So just substitute the value. So BOD 7 at 20 degrees Celsius is 150 milligram per liter divided by BOD 5 at 20 degrees Celsius. This is equal to 1 minus e raised to power minus K is 0.23 into 7 divided by 1 minus e raised to power minus 0.23 into 5. By solving this, you can get the value of BOD 5 at 20 degrees Celsius. Just do this calculation. So this is e raised to the power minus 0.23 into 5. 1 minus answer. Okay. So this is 0.683. This is 0.683. Now solving the numerator, this is e raised to the power minus 0.23 into 7. 1 minus answer. So this is 0.8. Okay. So 0.8 divided by 0.683 is 1.17. And 150 divided by this is 128.06. So BOD 5 at 20 degrees Celsius is equal to 128.06 milligram per liter. Let's check it once again. So this is e raised to power minus 0.23 into 7. 1 minus answer. Okay. So 150. Just once again check this. $128.06, right? So this is my final answer. Okay, so these are some of the questions that are frequently asked in the GATE examination. Please keep a check on all these questions. These are very, very important concepts that are frequently repeated in the GATE examination. I hope you have found this session very useful. I'll come up in the next session to discuss some more problems of the other topics. So that is all for the day. Thank you so much for listening patiently. Have a very good night ahead. Thank you so much.